Go.
Yeah, with this box, you can make electricity happen.
Oh, hello. I'm training for the World Cup. You know what hula hoops remind me of? Capacitors. Let's learn about capacitors.
Okay, capacitors. Let's talk about conductors first. What is a conductor? A conductor is anything that permits the flow of charge. Okay, metals are good conductors. This is because they have a structure, a lattice of nuclei and intershell electrons, which allow the freedom of charge to flow. Okay, and a capacitor is two conductors with opposite charges. Usually separated by a distance d, which can be a vacuum or an insulator, and this separation of charge creates potential energy. And so basically capacitors are storage devices for electrical potential energy.
Alright, so now we're going to take a look at capacitors and what happens when they charge in a circuit. So we're going to start off with a battery, a resistor, and a capacitor. The battery has a resistance of R and a capacitance of C. So we're going to go ahead and write our Kirchhoff proof first. So
3 seconds, new record, yeah!
E minus IR minus the voltage across the capacitor is equal to 0. So now we're going to look for the charging equation. So we're going to go ahead and first state that I equals dq dt, and Vc, the voltage across the capacitor, is equal to Q over C. Substitute in those terms, so dq dt R minus Q over C equals 0. So now we can solve for dq dt and change the rest of the variables. We can get dq dt equals E minus Q over C over R. So now we can solve this differential equation by using separation of variables. We're going to go ahead and say dq over E minus Q over C equals T over R. I'm going to integrate both sides now. We're going to integrate the left side from 0 to Q and the right side from 0 to T. We're also going to multiply both sides by negative 1 over C just to get the denominator a little bit nicer. Okay. So now we're going to end up with dq over Q minus CE equals negative dt over RC. So now when we evaluate this integral, we're going to end up with natural log of Q minus CE, this is from 0 to Q, minus natural log of negative CE equals negative T over RC. So using our properties of logarithms, we can say that this expression is going to equal Q minus CE over negative CE. And that's going to equal negative T over RC. So now we can solve for this Q term by raising everything to the E power, or from E. So we're going to end up with e to the negative T over RC equals Q minus CE over negative CE. So I multiplied both sides by CE, negative CE. And we end up with Q minus CE equals negative CE e to the negative T over RC. Then we add CE to both sides, and we end up with Q equals CE times 1 minus e to the negative T over RC. This is a function of time. So this is our charging equation for the charge on a capacitor as the capacitor charges in a circuit. We can now change our variables around and solve for V t in this case. So we know that V is equal to Q over C. So we can end up with, never mind. We can end up with E 1 minus e to the negative T over RC. We can also solve for I. We know that I equals dq dt. So if we take the derivative of this first expression with respect to t, we can end up with I equals e over r times e to the negative t over rc. And this term over here is actually our initial current. So we end up with the current in a capacitor is equal to the initial current times e to the negative t over rc. And these are our charging equations. Okay, so now that we've looked at the charging equation, we're going to go ahead and derive the discharging equation for a capacitor. So we've got a capacitor in series with a resistor of resistance R, and this capacitor is a capacitance of C. So we're going to go ahead and write our Kirchhoff loop now. We're going to have the voltage across the capacitor minus the current times the resistance of the resistor equals 0. So now we can substitute in some values. We're going to have I equals negative dq dt instead of positive dq dt this time, because the Q, the rate of change of the charge on the capacitor, is going down this time. So we're going to have a negative dq dt. And voltage across the capacitor is going to be Q over C. So if we substitute these values in and we put the IR on that side, we can get Q over C equals negative dq dt R. So now we can use separation of variables to solve this differential equation. We're going to end up with negative 1 over RC dt is equal to dq over Q. Now we integrate both sides. This side we go from the initial charge on the capacitor to some other charge Q. And on this side we go from 0 to t. So when we integrate this, we're going to end up with negative t over RC is equal to natural log of some value Q minus the initial charge Q sub 0 of the capacitor. So now we can use our properties of logarithms to simplify this a bit more. We're going to have natural log of Q over Q sub 0 is equal to negative T over RC. Now we can raise this side to the E, both sides to the E power. And then we have negative T over RC is equal to Q over Q sub 0. Multiply both sides by Q. And we end up with initial charge times e to the negative t over rc equals q. And we'll call this, and this is our function of time. So this is our equation for the charge on the capacitor as a function of time. We can also get the equation for the voltage across the capacitor by recognizing that q, or that v, equals q over c. So if we divide both sides by c in this equation, we'll end up with the initial voltage times e to the negative t over rc is equal to voltage as a function of time across the capacitor.
Alright, so this is problem 1983 E2. So, as you can read the question here, I'm not going to read it out loud, it's right in front of you. But, basically it's a RC circuit, and part A asks to determine the EMF of the battery. Okay. So part A, we're asked to find the EMF. So let's start off by writing the Kirchhoff loop. And that would be E minus the resistance here, let's call it R. R times I. Well, it says I at T, but we're given information of I is 0, and also we know that it's going to be minus VC, voltage across the capacitor, and that is one loop, and that's going to be equal to 0. But we know that at time t equals 0, there is no voltage in the capacitor, across the capacitor. And we also know that the initial I value is going to be equal to 10 microamperes, and so this is equal to R I naught, and we're given values of R and I naught, and we plug that in, we get 20 volts. Okay, part B. It asks to evaluate an appropriate integral and develop the expression for the charge on the right-hand plate of the capacitor as a function of time for t greater than 0. Okay, so we're just going to find, we're just going to use one capacitor, and we know that I is going to be equal to dq, positive dq dt, and because that is the definition, and we can rearrange that to find that dq is equal to I dt. Take the integral of both sides and get q is equal to I dt. In this case, we have the function of I here, and we simply plug that in, and we get, and we're going to integrate this from time 0 to t of, as not e to the negative t over 6 dt. Okay, I'm just going to move this up here, and doing some calculus, we get I naught, it's a constant, you can bring that out, and we get e to the negative t over 6 times negative 6. And we evaluate that from t to 0, and we get as naught times negative 6 e to the negative t over 6 minus a negative 6, which is plus 6. And what we get is 6 I naught 1 minus e to negative t over 6. Okay, part C. On the axis below, sketch a graph of the charge Q on the capacitor as a function of time. And we already saw that before from previous, we saw that the charge on a capacitor will start at 0, and as t approaches infinity, will reach a maximum charge based on its capacitance. And we already have a line here, or an asymptote, Q max, and so it's simply a function like that. Alright, so now let's talk about capacitance. We've already talked about the charging and discharging equations for a capacitor, but we haven't really discussed capacitance and the equations that go along with it. So capacitance is denoted by C and is equal to Q over V, where Q is the magnitude of charge on one of the conductors and V is the potential difference between the conductors. So let's say from A to B. And as you know, this charge is measured in coulombs and potential is measured in volts. And so what this gives us is farads, or simply F. Okay, next we have C equals Q over V. But since we're talking about capacitors where we have uniform fields, then we have V equals ED. So then we get this. Using Gauss's law, which I won't go into right now, we come up with Q equals sigma over epsilon naught times D. And if you remember, sigma is equal to charge over area, and so that would be E naught Q over, what is this, QD over A. Canceling out gives us E epsilon naught A over D. Okay, and this only holds true for parallel plate capacitors. Okay, so now let's talk about energy stored in a capacitor. Okay, energy. We already know that potential is the integral of, energy is the integral of potential. Potential energy is the integral of voltage. That is to say that du is equal to v dq. And what that gives us, integrating both sides, u equals v dq. And so basically, we have u equal to, we already know that v is equal to q over c dq. I'm going to integrate that from 0 to big Q. Now it gives us is 1/2, well, substituting in big Q, Q squared multiplied by the outside constant gives us 1/2 Q squared over C is equal to U. Using some simple substitutions, we have Q is equal to VC, and so U is equal to 1/2 V squared C squared over C is equal to 1/2 CV squared. We also know that that C is equal to Q over V, and so this could also be, cancel out the V's and you get 1/2 QV. And these are all the three equations you can use to find the energy stored in a capacitor. Notice that this is U for a capacitor, and the potential energy in anything else would simply be QV without the 1/2. Okay, so now let's move on to dielectrics. A dielectric is an insulating material that is placed between two plates of a capacitor in order to increase capacitance. An insulator. Okay, so basically, when you have a capacitor, it is the thing that you insert into it, and this always increases the capacitance. When we insert a dielectric, naturally the positive charges within the dielectric will move towards the top, the negative plate, so basically you have this. And basically you're going to have something like this. These will be the things within the dielectric, and there will be positive charges here. Basically it will be polarized inside, and similarly negative charges here towards the bottom and positive charges at the top. What this actually does is it induces an electric field opposite that of the plates, so it will be going this way, E induced. And so now we have that the E with the dielectric is equal to the E original minus E induced, let's just say EI. And let's just say that's equal to E over some factor capital K. Okay. So now we've established that E new is equal to E, the original, let's say it's a vacuum, over K. And since we know that V is equal to ED, we have that that V nu is going to be equal to, let's see, well, we can see that it's going to be equal to V of the vacuum over K. And this is because we have, well, let's see, when you substitute in, let's say, E is equal to over D's. So when you do nu over D is equal to vacuum, that says vacuum, over KD, D's cancel out and you end up with that equation. Okay. Okay, now we will go on to the capacitance. C is equal to Q over a change in V. We already established this. So now we have that C nu is equal to Q over V nu, which is equal to QK, dividing it, so it's multiplying by a reciprocal over the vacuum. And as we already established before, Q over V vacuum is equal to C vacuum, and so C nu is equal to kappa K C vacuum. And as we discussed earlier, C is equal to epsilon naught A over D, and so C nu is going to be equal to A kappa epsilon naught over D, or the equation caked. Okay, so now let's just quickly talk about dielectrics. Basically, when you insert a dielectric into a capacitor, the instantaneous voltage will basically decrease because you're increasing the capacitance, and yeah, and we have the relationship that U is equal to 1/2 CV squared. So as capacitance increases, voltage will decrease, and because V is squared and C is linear, the potential energy will also decrease when you insert a dielectric into the capacitor. Yeah.
Alright, so this is 1973 E1 problem. The plates of an isolated parallel plate capacitor are pulled apart very slowly by a force F. Each plate has charge Q and area A. Assume that edge effects are negligible. The spacing X is much smaller than the parallel dimensions. So A, determine the change in capacitance as X increased by dx. So A, since capacitor equation is A K epsilon naught over D, and we know that dielectric of this is just 1, so it's going to be A as epsilon naught, and D is X, so it's dx. And we can get the derivative of this. We get A epsilon naught over negative x squared. So, and the B asks, determine the change of stored energy in the capacitor as x increased by dx. So, energy is 1/2 CV squared, or 1/2 Q squared over C. So, we can plug C into here, so we get 1/2 xq squared over 2 A epsilon naught. And we can get the derivative of this, so du over dx is just going to be Q squared over 2A epsilon naught. And so C asks, how is the force F related to the change in stored energy? Determine F in terms of X, Q, and A. So C, work is 1/2 Q squared over C, and it's equal to F dx. And we can get the derivative, integral this side. It's going to be 1/2 Q squared over C and F x. And F is going to be 1/2 Q squared over C.
Okay. Okay.
Hello, ladies and gentlemen. So we're gonna do number 2 that was on our RC circuit test. It's this one. This problem. Alright, so part A is asking what's the dielectric constant. So we can use the Cake equation. And then just with some algebraic manipulation, we get K is equal to dc over A epsilon naught. Then we just plug in, distance is given as 10 to the negative third meters, so is equal to 10 to the negative third times the capacitance, which is given as 5 times 10 to the negative eighth farads, over area, which is just 1, times epsilon naught, which is 8.85 times 10 to the negative 12. And if you multiply that out, you get K is equal to 5.64. Okay. Part B doesn't really have much to do with capacitance and dielectrics. That's more to do with RC circuits. So we're going to skip that part and go straight to part C, which is asking that after the fully charged capacitor is disconnected from the battery, and you leave it isolated in space, and you remove the dielectric, what is the new voltage across the plates? That's question C. So again, so what you have to do here is you know that the C new, it's just going to be 8.85 times 10 to the negative 9th. And we know that just because of the Cake equation again, because C is equal to area K epsilon naught over D, and K is just going to be equal to 1, so you can plug in for each of these, and you can get C new, and that's what this is equal to. And Q is equal to 1.5 times 10 to the negative 6, and that's just something you found in B, in part B, so we're just going to put that in there. It doesn't really have much to do with dielectrics, but you just need it to solve the problem. So next we're going to look at the equation Q equals CV. So we're looking for the new voltage. So Q over C equals V. You plug in this for Q and this for C, and you get the new voltage is equal to 170 volts. So that is your new voltage. 2D doesn't really involve any writing, but it's asking if there's now more energy stored in the capacitor, where did it come from? And if there's now less energy, what happened to it? And there's going to be more energy because you have to do work in order to take the dielectric out of from between the two parallel plate capacitors.